cars. We would like to know if there's an accident that happens.
All right, welcome everyone. So today we're going to be talking about interpretable
what was the
deep learning.
So that
And
we can
most of the
then
slides are coming
attribute
from
the
Seung-Tai,
fault to the
who has a
machine
beautiful
learning
lecture from
or
this
to the
from
conditions
2018,
or to the insurance
and they've
company
been
or
slightly
perhaps to
modified here.
adversarial
So
features
we're going to
in the
basically
map that
look
trick the
at
machine
how
on
are
purpose.
all of these beautiful models that we've been building making mistakes, or how are they right? And can we interpret what they're actually learning? So we're going to first look at definitions of interpretability. How do we convert implicit neural network information to human interpretable information? Why is interpretability important? For debugging, for making discoveries, for the right to explanation. When somebody said, oh, sorry, you can't have a mortgage, I would like to know why I can't have a mortgage. And we're going to talk about both ante-hoc and post-hoc methods for interpretation. So ante-hoc methods for interpretation are basically forcing the learning itself to be done in a constrained way, so that only interpretable models are learnable. And post-hoc basically says, well, we're going to build super complex models, and then we're going to go back and interpret them, and we can interpret them at different degrees of locality. Then we're going to look at different ways of interpreting deep neural networks. So interpreting models versus decisions. Interpreting models is macroscopic and focuses on understanding the internals of the model, whereas interpreting decisions is microscopic and is focused on the practical applications. Then we're going to look at specifically the first part of interpreting models and 4 different methods for doing that. So weight visualization, building surrogate models that approximate the black box but are interpretable. We're going to look at activation maximization, basically looking at where is the most activation coming from. And then we're going to look at example-based models. And then we're going to look at the second part of interpreting decisions. And again, example-based models, attribution methods. So why are particular gradients noisy? And 2 different types of gradient attribution, both smooth grad and interior gradient, as well as different methods for backprop-based attribution, so deconvolution and guided backpropagation. And then we're going to look at how different attribution methods can actually be evaluated, both qualitatively through coherence, so whether the attributions highlight discriminative features and objects of interest, and through class sensitivity, whether the attributions are sensitive to particular class labels. And then we're going to look at quantitative sensitivity by removing features with high attribution and observing whether there's indeed a large decrease in the class probability. And then we're going to look at remove and retrain, and then keep and retrain, so that we expect that if there's low class probability because a particular image was not seen, that removing the pixels, retraining, and then measuring the accuracy should be able to drop. So let's dive right in. Why interpretability? So what is interpretability? So when Lee Sedol was basically playing against AlphaGo, he has this beautiful line where he basically was describing that there were, non-human moves that basically, and then he came out saying, wow, I've spent, humanity has spent thousands of hours and, hundreds of years playing Go, and yet we did not get it at all. So the machines are basically telling us that there's something deeper about the game, but AlphaGo itself wouldn't say what's deeper about the game. It would just crush all human players and all machine players. So there was something that the machine was learning, but that we could not extract knowledge from. So being able to interpret deep learning methods that outperform humans should hopefully be able to give us some insights as to why are the machines doing so much better? What are the tricks? What are the insights that we can learn from that? Looking at image classification, looking at self-driving cars, we would like to know if there's an accident that happens, why did the car turn right? Or why did the car not brake? Or what was the interpretation? So that we can then attribute the fault to the machine learning, or to the conditions, or to the insurance company, or perhaps to adversarial features in the map that trick the machine on purpose, and so on and so forth. When diagnosing disease, you don't want to show up at your doctor's office and the doctor says, oh, take these pills. And you say, why? And the doctor says, I have no idea. The machine told me. So what you would like to know is, why did the machine say that? Why did the machine make a particular classification of a tumor as an aggressive, leukemia, for example, and then why are particular drugs prescribed, or why is the diagnosis such, and why am I saying that the patient will die tomorrow? We would like to know, because then that can actually teach us about, number one, how to make better diagnosis in the future. Number two, how to question the particular diagnosis for these patients. And number three, how to overall understand the features of the model to then train, either better feature selection or better classifier, or to be able to even teach humans how to make better predictions. With machine translation, you'd like to know why are particular texts translated a particular way, and so on and so forth. So interpretability is extremely, extremely important. And the typical approach to machine learning has been, you build a giant data set, you throw a ton of compute power with a giant model, and you don't worry so much about how and why these models work. All you care about is that you can do classification, you can do localization, you can do object detection, you can do segmentation. But at some point, you would like to know how and why are these working the way they are for all of these different reasons. So what we would like to do is extract some interpretable information from these black boxes. So this can be helpful for verifying whether the model works as expected. So because wrong decisions can actually be extremely costly. Do you want to ground every airplane? Do you want to sort of, park every self-driving car when there's an accident until you figure out what happened? Or do you want the model to say, okay, here are the specific conditions under which I was not able to make a decision? And also, if there is mixed classification, you'd like to be able to attribute that to specific features of either the data or the model. So with standard machine learning, you basically have your data, you build your machine model, and then you have your predictions with some, test error, training error, generalization error, and so on and so forth. With interpretable machine learning, you would like to have some interpretability extraction from your machine learning model, and then be able to inspect by a human what the model is actually learning, and then give feedback either through the data or through the model from the interpretation of those mistakes, from the inspection of whatever is happening inside the black box model, and then have a set of verified predictions. So basically you're optimizing not just for generalization error, but also for the human experience. And that's sort of what interpretable machine learning is all about. And then the next goal is, of course, to gain insight as to what is the machine learning about this, image of a tumor that we can then train our doctors to recognize and sort of have the combination of human and machine working together. So we'd like to learn about the physical, the biological, the chemical mechanisms of disease, which is what this class is going to be mostly about, and then understand, not just how our brain functions, but also how are we as humans making decisions when we are looking at images. So I don't know if you remember those slides that we got a lot of comments on with the muffins versus the chihuahuas, and then the bagels versus the the wrapped up dogs. A lot of people were like, wow, I'm learning about how my own brain functions by looking at these images. So it's kind of cool to sort of learn more about perhaps how we solve particular complex tasks. And then, as I mentioned earlier, the right to explanation. For example, if the algorithms are trained in discriminative ways, if, for example, the color of the skin of a person is taken into account in a hiring decision, or the income of their parents is the primary factor in what school they get into, you would like to be able to abolish these biases. You'd like to be able to sort of systematically fight the biases that are unfortunately inherent in all of the training sets through decades of discrimination and centuries of discrimination in not just the US, but across the world, to be able to say, this is why the model is making these predictions. Let's eliminate all of those biases and then sort of have an algorithm that's clean of those biases and hopefully can outperform what training data sets have been biased by. So Again, the US has an Equal Credit Opportunity Act. The European Union has a General Data Protection Regulation. France has a Digital Republic Act, which are aiming to not only make these unbiased decisions, but to also be able to justify to every person who is the subject of one of those decisions, why was that decision made? And that's the right to explanation. So before I go further, I'm gonna sort of see who's with me so far. Let's see. Lovely. We're at 90%, 10%, 0, 0, 0, 0. This is awesome. Okay, so there's, as I mentioned earlier, two types of interpretability. The first interpretability is to build interpretability into the design of the model. To basically choose interpretable models to start with and then train them and just be satisfied with whatever accuracy they achieve. So the decision tree could be, you know, am I hungry? Do I have $25? Do I go to the restaurant, buy a hamburger, go to sleep, etc. So if the model is expressive enough, then, you know, we're good, because that basically allows us to say, every time I made a decision, I know exactly through my decision tree why the decision was made. But the problem is that these decision trees are ridiculously constrained and totally underpowered with most you know, real world data sets. By contrast, deep learning has millions of parameters. So we're not going to build interpretable models to start with. What we're going to have to do is build post hoc interpretability. So basically, we're going to build these complex models, and then after the fact, develop special techniques for interpreting what the models are actually doing. So one is anti-hoc. So basically, before you see any data, you basically build interpretability into the model. The second one is post hoc. After your model is trained, then you say, oh, okay, great. Now I have the black box. Let me figure out what's happening in the black box. Everybody with me on this one? Great. Awesome. So again, 83, 13, 400. So again, we have millions of parameters for most of these deep learning models. So, you know, these have been increasing both in, you know, just space, complexity, parameter complexity, training complexity, data set requirements, etc. So what we're going to need to do is find ways to actually interpret those. And we can classify, or at least gradate, post hoc interpretable methods based on their degree of locality. So all the way to the top, at the model, we can ask, what are the representations that are being learned by the model? So basically, how do I recognize edges and eyes and ears and, you know, wheels? All the way down, you can ask, why is a particular input classified this way? And what are the pixels that are contributing to that classification? And then in the middle, you can basically ask, at intermediate representations, what are the patterns or the images that maximally activate a particular neuron? To basically say, dumbbell, these are the activation functions. And sort of we're going to look at different levels of post hoc interpretability at each of those levels of resolution. So you can think of them at the model level as what is the entire function X that I'm approximating when I'm distinguishing these blue dots from the green dots. What is the boundary of classification, for example? In the intermediate level, you can say, well, what are some features that are true to all inputs that are blue? And then they're classified as, I don't know, car. And the last one is, why was this particular example of a car classified this way? All right, so we basically define interpretability, basically converting implicit information to human interpretable information. We looked at the motivation for interpretability to, number one, verify that the model works as intended, to be able to debug it, to make biological discoveries or get insights about the particular class of objects that we're classifying, and also the right to explanation. And then we distinguish both anti-hoc, which are training interpretable models, and post hoc methods for interpretability, which are focused on interpreting complex models after they've already been built. And we saw this gradient of the degree of locality. So let's dive right in and look at what are ways of building interpretable neural networks, both at the model level and at the decision level. So again, we're going to be looking at the whole gradient from the model level all the way down to the individual object decision. So we can broadly classify these as interpretable models that are either interpreting the model itself or interpreting the decisions. And then the decisions can be based on either attribution methods that are basically saying why, what feature gave rise to this particular decision, or example based that are basically explaining what are the primary examples that were leading to a particular decision. And then on the model side, we're going to look at how to analyze the representations themselves and how to generate data from the model and how to understand these examples. So at the level of interpreting models, we call these macroscopic because they're looking at the whole class of, the decision boundary that we showed earlier. And these are going to be, we're going to look at different ways of doing that, which are going to be either summarizing this deep neural network with a simpler model, for example, a decision tree, and then approximating not the reality of the world, but the decisions of the model. So the model is presumably learning a quote unquote cleaned up version of the world or a modeled version of the world. And we're going to be approximating that model rather than the real world. We're going to be looking at ways of building prototypical examples of categories and finding the patterns that maximize the activation of individual neurons at different levels in the hierarchy. So we're going to be seeking to better understand the internal representations of the model using these macroscopic models. And then for the microscopic, we're going to be asking, practically, why did the deep neural network make this particular decision? Verify that the model is indeed behaving as we expect, and then finding the evidence underlying a particular decision. So we're going to be basically using this two-level hierarchy to go through these two types of models, okay? So on the second level, we're going to be looking at representation analysis and specifically weight visualization, as well as building surrogate models and so on and so forth. All right, so now let's look at interpreting models. So basically focusing on the internal representations of the model. So we're going to look at 4 types of approaches. Number 1, how do we analyze the representations? So basically, how do we visualize in an image format the internal weights of our deep neural networks? How do we represent the neural network using an interpretable model, what we're going to call a surrogate model? And then how do we understand the inputs that maximize particular activation units? So how do we generate data through this activation maximization approach? And then how do we focus on particular examples that were the most important in those decisions? So again, we're here in the interpreting models part, and then we're going to turn to interpreting decisions. And now we're diving into representation, data generation, and example based. And then representation is going to be split into weight visualization methods and then surrogate model methods. So just looking at what are the features that are extracted from an image when I'm learning that this is a car. And this is extremely insightful, and this is something that has truly transformed the field of deep learning by being able to actually peek inside the quote unquote brain of a deep learning method. So if you remember from the convolutional neural network lecture, I sort of distinguished the left half and the right half of the model. The left half was all of these layers of convolutions, and I called that left half representation learning. And then the right half was just the classification. Basically, now that we have extracted these levels of hierarchical features, from these features, we're making a decision as to whether it's a car, a horse, or a person, or an airplane, and so on and so forth. Okay, so we would like to know, how are these deep learning models making these inferences? What are the internal representations that they're making? And that's where this has been extremely insightful, to basically realize that if I take individual neurons and I back project onto the image, what are the features that these neurons are learning, then what you see is extremely insightful. It basically tells you that indeed, just like the motivation of, hey, let's figure out how the animal visual cortex works by looking at sort of inside the brain of a cat or a monkey, and then understanding how are individual neurons firing when I show a cat an edge facing this way or that way. We were able to understand back in the 50s and 60s that in fact particular orientations lead to responses at particular neurons. That's what you're seeing here. These are neurons that fire when there's an edge this way, and these are neurons that fire when there's an edge that way, and so on and so forth. And there's other neurons that fire when there's a circle or a change of gradient from one color to another color. I mean, this is extremely insightful and quite striking that indeed the visual system and the artificial convolutional neural networks that were learned purely from scratch without hard coding any of these features are in fact recognizing primitives that are interpretable to humans. Okay, so I hope I'm not the only one excited here, but let's see, who's excited about looking inside the brains of a neural network? Okay, awesome. I'm not the only one excited here. So 63, 26, 704. I do have one yawn, which is great. Okay, so we can basically visualize the filters in a convolutional neural network, and we can understand the kinds of features that CNN has learned. But the problem is that there's still way too many filters. We have 5 million parameters, and we have thousands upon thousands of internal nodes. So we don't want to go about visualizing every one of those to sort of understand, why do I see a car when I see a car? So what we can do is start diving a little deeper and basically sort of looking at different ways of extracting more information about particular decisions. So for example, we could summarize the deep neural network with a simpler model. For example, I could use a decision tree, or I could use a linear model or a graph that basically sort of decides, perhaps, not perhaps, but certainly not as accurate of a model, but something that is more directly interpretable. So these are known in different papers as meta models or approximation models or response surface models or emulators. But the key idea is that we're going to train an interpretable machine learning model on the outputs of our black box model with a specific goal of interpreting it. It's not going to be exact, but it's going to be close, hopefully, and interpretable, certainly. So we're deciding to use a simpler model to approximate not the real world, not the actual real world, but the predictions. And again, this is model agnostic. It doesn't matter what my black box is made of. I'm going to use a simple model that is both independent of the original world and independent of how the black box actually works, just based on the outputs of that. Okay, so who's with me so far on sort of what we're going to be doing here? So let's see. Oops. So what we're going to be doing is training a model on the output, not on the input, but on the output of our black box model, and then trying to understand how are the decisions made using this parallel model that sort of tells us, oh, well, it's here. It seems that these are the particular decisions that are being made. Okay, so we're at 50, 41, 10, 0, 0. Okay, so that's surrogate models. And then perhaps the most exciting so far has been this activation maximization. So we're going to be generating data, but almost backwards from our model. So we're going to be finding patterns that maximize the activation of a particular neuron. Okay, so if I'm trying to classify a particular bird here, then I can say, okay, well, the neuron called goose is activated maximally based on these types of images, okay? So what we're going to be looking at is how to maximize among all possible inputs the input X that maximizes the probability of generating the particular weights for that particular class. So basically, the weight of that class, given my parameters, is going to be maximized by that input. Okay, so who's with me on this one? So we're maximizing over all possible input parameters the parameter that maximizes the class conditional, the class posterior probability for that class. Okay, so everybody with me on the left part of this equation? So I'm searching over all inputs for the input that maximizes that class. That basically says goose is maximal here. Okay, so we're at 30, 36, 25, 11, 0. Now, on the right side, this is the constraint under which we're going to be doing this maximization. So we're going to be using a regularization term that is basically going to tell us, I don't want to choose any possible input, but I want to choose inputs that are actually meaningful. Because basically when I see this, well, I'm not so excited about this model of a goose. Instead, what I want to see is something that actually to the human eye resembles a goose. And that's where the regularization term comes in, okay? So if I only maximize based on the class probability, I'm going to get images that don't make much sense. But if I maximize using this additional regularization term, then I can constrain the output to also be, human interpretable. So this is where deconvolution comes in, and that's where sort of running the convolutional models backwards, will come into play. Not yet, but shortly. But basically, what we're looking for is an X star that maximizes this class probability of which character am I recognizing between which digit between 0 and 9. I want to recognize the digit 3. And then this is, one feature that is actually interpretable within that constraint. So we want to maximize the X that maximizes the class posterior probability, but under the constraint that this X is actually human interpretable. So if we're basically iterating over this search for both the maximization of the class and also a regularization that basically tells us, make sure that this is as close as possible to the actual inputs or to the, sort of human interpretable classes. And we're going to see a lot more of that when we start thinking about latent variables and latent parameters that are basically perhaps telling us, is the 3 tilted this way, tilted that way, stretched, etc. So we can actually have intermediate latent parameters that sort of parameterize this otherwise noisy vector that I would normally get. So this is the initial solution, and then you can see that it's very blurry, and all of the characters are basically, just, very messy. And after lots of training, you start seeing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, sort of the solutions that we're converging towards. But again, those are not very pretty. These are still overlays of all of the possible activation functions that distinguish that one character from all of the other characters. So they're not very useful. And similarly, the representation of a goose versus an ostrich, again, is not very useful. So what we're going to need to do is redefine our optimization problem to include that additional constraint. So again, this activation maximization in this data generation box builds typical patterns for given classes, for example, beaks and legs. And the goal is that unrelated background objects are not present in the image. But the disadvantage is that what we're getting out does not really resemble these class-related patterns, and it actually lowers the quality of the interpretation for the given classes by sort of seeing this overlay of characters that to the machine makes a lot of sense, but to the human doesn't really make much sense. So what we're going to be doing instead is forcing the generated data X star that maximizes that function to match the data more closely. Instead of finding the input pattern that maximizes the class probability, we're going to find the most likely input pattern for a given class. So that's very different. Instead of sort of searching over unlikely patterns that just simply do not occur in the training data set, because no one takes pictures like these and no one writes characters like these. We're going to basically ask for the most likely input pattern for that class. And then the most likely is the key here. So we're now going to look for not just the maximal, but the likely and maximal. So basically the maximal one among the likely ones. Who's with me on this subtlety of we're not just looking for any kind of artificial construction of a set of pixels, but we're looking for an actual handwritten character that could have been generated by one of the humans entering input. Okay, so 40, 40, 20, 0, 0. That's great. Okay, so instead of finding the input pattern that could be somewhere around here, or somewhere way out here, that maximizes that classification distinction, instead we're going to be looking for an X star among the likely inputs entered by users to find the most likely input pattern for a given class. So that's where this constraint is coming in. So instead of maximizing this alone, which would basically give us anything anywhere, we're basically maximizing things within the space of class generations, okay? So again, we can look at either an activation maximization with, some original constraint, or an activation maximization within the space of possible inputs. And then these techniques require an unsupervised model of the data, either a density model that basically tells us where is the data most dense. So some kind of, feature density distribution that basically tells us we're going to sample from within the realm of possible inputs rather than, way out here. Or a generator function that doesn't need to have the full data distribution, but is able to sample from that distribution without necessarily explicitly representing that entire distribution. Okay, so these are going to be the two techniques that we're going to be using. And if you look at now this original set of characters that were maximizing the activation of a particular node, they were completely uninterpretable. So this is just the simple activation maximization where you initialize it to the mean. And then you can look at multiple progressions of this where you can initialize to the class means. And then suddenly this is much more interpretable because you're now constraining your X star to come from within that distribution. So basically within the mean of that distribution by modeling that distribution explicitly or by sampling from the probability density function of that distribution, even without modeling it explicitly. So this is looking at just, a very simple AM. This is looking at density of activation maximization. So basically you initialize to the class means, but you're taking the full density function. And then you can basically build a generative model that generates individual characters by sampling from that mean. And you can see how connecting this model to the data leads to much sharper visualizations, okay? So instead of looking at something like this, we basically have, images of a mosque, which, you can kind of see the minaret next to the, central mosque. You can see lipstick and, particular birds or beetles and so on and so forth, where these are not quite images. These are not quite natural images, but they're immediately more interpretable by sort of forcing your representations to be within the code space rather than, anything that could be coming from outside. Okay, so who's with me so far on the difference between this unconstrained activation maximization and this constrained activation maximization, and more generally, how is activation maximization and data generation in general going from the model back to look at the images that sort of maximally generate particular features can be helpful here. All right, so we're at 40, 40, 20, 0, 0. All right, so then we looked at multiple ways of building interpretable models, looking at the internals of the model. So we looked at weight visualization. We looked at building surrogate models that sort of approximate the particular output. We looked at activation maximization under the constraint of being sampled from the input distribution. And now we're going to turn to example-based. So to basically interpret these models, what we can do is find image instances that either represent or do not represent the image class. So we can look at maximum mean discrepancy and a method called MMD critic that was actually developed here at MIT and presented in NIPS in 2016. And selecting prototypes efficiently to basically classify the nearest prototype for a positive or a negative example. So basically, as you're looking at digits, you can basically say, well, here are the near misses. This is something that, again, Patrick Winson has always talked about. How do I learn the concept of an arch? Well, I want a near miss, what's not an arch that is informative. And this is what sort of the machine learning community is doing when looking for these near misses, for these, characters that are misclassified, but close to the particular input. So all of these can basically teach the model how to improve, and you can sort of learn what are the mistakes that it makes and why is it making those mistakes. And by feeding it those criticisms, you can then improve the model to be better. For example, when classifying two dog breeds, you want to find the closest dogs to that breed that are not that breed, to basically then recognize the salient features of that breed that distinguish it from the near misses. And if you look at, misclassifications of dogs, you want to say, well, why did it misclassify it? And usually these are dogs that are in costumes. And then those criticisms, those misclassifications can basically tell you again, why am I making these mistakes, and, sort of better improve the model or not. And then you can see here, based on the number of prototypes, how different methods, reduce their error based on, particular global or local features for this maximum mean discrepancy approach. Okay. So we basically looked at either visualizing the weights of the different layers of the neural network directly. We looked at building surrogate models that are perhaps not as accurate, but are more interpretable. And we looked at how we can look at activation maximization at sort of generating the features that are the most informative. And then lastly, how we can select particular examples for both prototype images and also prototype criticisms, which are the most informative for distinguishing that particular class. Okay, so let's see who's with me on that whole section. So all right, so 40, 46, 15, 00. And then one more poll up. Who feels that they've learned something? Lovely. Okay, so we're at 55, 41, 00. And then there's the one person who keeps me honest. Nope, I really don't see why the professor is all excited all the way at the bottom. So the polls are anonymous. I will never figure out who you are, but keep being honest. This is awesome. I need this. Okay, great. So going back to our outline, we saw why interpretability is so important. We saw first the model side of interpretation, where we're looking at the macroscopic understanding the internals of the model. And then we saw 4 different ways of doing so: weight visualization, surrogate models, activation maximization, and example-based. We're now going to turn to the second part, the microscopic, looking at practical applications of why is a particular decision made. And we're going to again go through 4 different ways of interpreting decisions made by the model. We're going to look at example-based. We're going to look at active attribution methods. Why is a particular gradient noisy? We're going to look at gradient-based attribution with smooth grad or interior gradients, and then backprop-based attribution with deconvolution and guided backpropagation. All right, so now looking at the limitations of model level interpretation. So basically, the challenge, of course, is what would be the best image to interpret the class motorcycle. So we've, looked at ways of generating not just one sort of superimposed mess, but instead sampling from the input distribution. But the challenge, of course, is that the input distribution is extremely diverse, and any of these might be preferable by different people. For example, an aficionado of motorcycles might think that this is actually the thing that triggers motorcycle most to them because they're used to driving them, and different folks might be sort of more amenable to sort of different best representative of the class. But I would argue that all of them are almost equally representative. So summarizing a concept or a category as complex as motorcycle into a single image is extremely difficult. And a good interpretation of what is the model learning when it's learning, motorcycles would be as large as the diversity of the concept that it's trying to interpret. So basically, when we're learning through multiple layers of our deep neural network, the concept of a motorcycle at layer, 20, we would like to know sort of what are all of the different examples of that class. So the questions that we're going to have that are not as very well answered through this model interpretation is, how do we find a prototype? Basically, how does a motorcycle typically look like? And, sort of going through all of this to decide on motorcycle or motorbike, what is the, typical one? And then the second challenge is, how do we justify our decision? Why was this particular example classified as a motorbike? So what in our sort of many, many layers led to that example being, motorbike? So can we justify those decisions? And that's what interpreting decisions is going to be all about. So basically, how do we attribute those decisions to either the gradients or the backpropagation or particular examples? So we're going to look at 4 ways of interpreting decisions that the deep learning models are making. The first is going to be example based. Then we're going to look at attribution methods. So why are the gradients noisy, for example? And then gradient based attribution and backprop based attribution methods. So let's dive in. So basically, example-based is asking which training instance influenced the decision the most. So if I'm classifying this as a sunflower, then I'd like to go through all of my training images and sort of say which of these images influenced this decision the most. And, perhaps this image of a sunflower was not contributing that much to the class, to the learned class of sunflower. But this image, it turns out, contributed greatly as a training example to the weights that were learned when ultimately classifying this image here as sunflower. Okay, so it doesn't tell you what features of this image were important in classifying it as a sunflower. It tells you what input images from your training set were in fact the most informative. So it does not specifically highlight also what features of those images were the most important. And again, these are influence functions for interpreting these black box methods. So they're, basically studying the fragility of these neural network model interpretations can be, extremely helpful through these examples by basically saying, okay, well, I can't tell you how I learned what a sunflower is, but I can tell you which images contributed to this particular classification of a sunflower. And that's extremely important because you can basically say, well, if I'm classifying a dog as a sheep, I can go back and say, well, here are the images that you called dogs that I used to classify this as a sheep. So it basically tells you the nearest images in a way, not based on pixel proximity, but based on influence on the classification of one particular image. Okay, so let's see. Who's with me so far on this concept? So basically, we're not asking what are the pixels of this image that made me classify it, but we're asking among your enormous training set, what were the images that influenced your decision for that image the most? All right, so 43, 57, 00. Okay, so that's example based. So it's basically going back to individual examples of your input training set that sort of we're guiding that one particular decision. Okay, so this is very much like in law. You basically, so the Supreme Court will say, well, based on the decision in 1956 of this versus state, we have postulated that, this is now guiding our decision for, the verdict that we cannot convict this person or something like that. So this is, the same thing, but now through the training examples of a neural network. All right, so that's example based. The second one is looking at attribution methods. So given an image, X, and given a decision, this is a 3, based on sort of these activated pixels here. The question is, can we assign to every pixel, X1 all the way through Xn, an attribution value that basically tells us, how much is that particular pixel influencing this decision of calling this particular character a 3. Okay, so this is orthogonal to our deep convolutional neural network. So basically, for any deep neural network, you have some kind of function. And then what we would like to infer is an attribution score that gives us for every single pixel, what is the weight with which that pixel is contributing to the classification of that input image, okay? So you can visualize these attributions directly on the image. You can basically say, well, for every pixel of the image, I have a score. So why don't I directly visualize that score? And what you can see is that the junctions here, specifically in the 3, are in fact the strongest contributors to the decision to classify this image as a 3. It doesn't tell me what a 3 looks like, but it tells me for this particular image, why did I classify it as a 3? So for example, when the self-driving car crashes into a tree, you can basically say, well, why did you decide to turn? And you can go back and say, well, these are the pixels in my image or in my video stream that basically made me decide that, turning right was the right class for that element. So basically, we're going to be looking at how are these individual pixels for this particular image and for that particular class responsible for making the decision. So we're basically feeding this through the function and then working backward from the function to basically say, what are the pixels that were the most informative for that? So you can visualize these attributions as heat maps in, a 5x5 pixel image or in much more complex images. So for example, if your label is, garter snake, then you can basically say, well, what aspects of my input were the most informative? And now you can look at different gradient-based methods and sort of ask what were the pixels that were contributing to that particular decision being made. And this is extremely informative. This is, again, the goal is interpretable machine learning. So the goal is to sort of say, well, what aspect of my image led to the decision of classifying this as a snake or turning right in the rain and so on and so forth. And then you can see how the pixels are in fact concentrated surrounding this snake, but not exclusively on the snake itself. So there are some features that are basically saying, well, it turns out that the background, the fact that the snake is usually surrounded by something dark, is in fact informative to making the decision of it being a snake, and so on and so forth. Okay, so this is very informative because it basically tells us that it's not always the pixels within the snake itself, but it's the surrounding image as well that are contributing to that classification. So we can basically use this to build a saliency map to basically tell us what are the pixels that are the most salient in an image. So you can have a baseline attribution saliency map that basically tells you about the gradient of the decision of the classification function of that particular image with respect to a given input image X. So you can basically calculate that saliency as the gradient relative to X of this function, which is basically the partial derivative of this function relative to that one particular image. So we can calculate that saliency based on the same exact methodology that we've developed for backpropagation. Basically, when we were doing training of our deep learning models and we were updating the weights, we were going through the exact same math of taking the derivatives relative to the weights, but now we're taking the derivatives relative to the pixels of that particular image. So we're now calculating the saliency map using the exact same propagation, but instead of derivatives relative to weights, we're now looking at derivatives relative to pixels. Okay. So who's with me so far about what we're doing on the saliency? We're basically now going to be asking, how did I classify something as a snake? By looking at every pixel and how much is contributing to that classification, by taking the gradient back through the classification function f, and then attributing that back to individual pixels of the image, and then visualizing these pixels as heat maps through this function. All right, so 36, 50, 14, 0, 0. That's great. So this is the first attempt. So basically we can see that, oh, well, great. There's something surrounding that machine and something surrounding these, baboon and something surrounding these buffaloes and this temple and so on and so forth that basically leads us to make the particular decisions that we're making. But the problem is that these saliency maps are very noisy. You can see that there's like scattered pixels all over the place. It doesn't tell you, well, hey, here's the contour of exactly what I would expect a water buffalo to look like. Okay. So they're only roughly correlated with the object of interest. So the question is, how can we actually improve these saliency maps? And also, why are these saliency maps so noisy? And in fact, the second question is going to guide the first question. Namely, we're going to postulate different reasons why they might be so noisy and then develop methods that address each of these reasons in turn. Okay, so let's now try to understand, why are these maps so noisy? So the first hypothesis is that indeed saliency maps are actually truthful, and that certain pixels that are scattered randomly across the image are in fact central to how the network is making the decision. And that noise is in fact important. When I'm classifying a gazelle in the Serengeti, the gazelle pixels are as important in my classification as the fact that I see gazelles usually in the Serengeti. So perhaps my eyes, as they're making the decision to classify this gazelle as a gazelle, are in fact guided not just by the pixels in the gazelle per se, but also by the pixels in the surrounding. Kind of like we saw earlier, the pixels that were actually being highlighted here were in fact dark pixels surrounding that snake. And that might be because we see snakes usually in dark places or in sort of light and dark places, suggesting that they're hiding. And that might actually be part of that activation. So that's the first hypothesis. Well, there's a second hypothesis, which is that the gradients might simply be discontinuous. Our deep neural network actually uses piecewise linear functions, such as ReLU, the rectified linear unit, max pooling, etc. And basically the gradients are in fact, zero everywhere in that, so basically if you look at the ReLU function and how I'm taking the gradient through the ReLU function, this rectified linear unit has derivative exactly zero everywhere in the entire negative space. So it's very hard to sort of run smoothly through this space. So, maybe the challenge is that the gradients are actually discontinuous and that these activations and max pooling, which is basically saying, well, I'm going to take the maximum of anything that activated in that entire part of the image, are in fact not conducive to this smooth gradient learning. And the reason why everything looks so noisy is because I just couldn't very reliably figure out a very clean gradient through the space. And basically, perhaps the sudden jumps in the importance score are due to infinitesimal changes in the input that are basically, jumping up and down. So if you look at the layers of that neural network with, 3 layers, the function can be somewhat smooth. The function that I'm learning can be somewhat smooth, and sort of learning these gradients might actually be feasible. But as I add more and more layers, then the firing of whether something is a gazelle or not is extremely discontinuous. It basically jumps up and down extremely rapidly based on subtle variations of the input. So you've probably all heard about these adversarial examples where I can actually modify the pixels of an image of a gazelle in ways that are imperceptible to the human eye, but then will make this gazelle classified as a, I don't know, a German tank. And, this is related to that in the sense that this is not a smooth function. Basically, because there are so many different layers, I can actually trick the classification function by sort of choosing one of those local minima and sort of, moving the pixels down that way to actually carry out misclassifications. So the second hypothesis is that perhaps our gradients are actually discontinuous, and there's so much noise because of the number of layers and because of these sort of not easily, derivatable functions, that the functions whose derivative cannot be easily taken. Okay. So let's see who's with me on this concept here about the discontinuity of the gradients and sort of how this is contributed to by both the piecewise linear functions and by the many layers of our neural network. Awesome. So 44, 40, 15, 40. Okay. So the third hypothesis is that perhaps our function actually saturates. Maybe a particular feature may have a strong effect globally, but have a small derivative locally. So because, this particular feature is having most of its activation here, the derivative is not quite able to capture that one aspect. So basically, this function has already maximally fired and it can't fire any higher. So I've kind of saturated here and I can't, learn anything smoother at that point. Okay. So these are our 3 hypotheses that we're going to be working with. And then using these hypotheses, we're going to say, well, how can we actually improve the saliency maps? So how can we basically improve on this partial derivative with respect to the input? So we're going to look at different ways of modifying that function to basically ensure that the results are not as noisy. So one possibility is to actually add noise to perturb the input to some other input, and then use the gradient on some perturbed input. Okay. And there's some methods that actually take the average over the perturbation set. So instead of just doing one perturbation X star, you basically do multiple perturbations. So I take my original image and I perturb it in a bunch of ways. And based on that, I'm going to try to actually smooth out that gradient by sort of not looking at one particular image, but by looking at an ensemble of images that are near this particular image, and then asking, well, perhaps for this one particular instance, the activation function is noisy this way. And for another instance, it will be noisy another way. For another instance, it will be noisy another way. But if I take the average over multiple activations, then maybe they will converge on the actual pixels that seem to define the gazelle more directly. So how about we take a 60-second stretch break? So Jackie, you did such a great job last time. Do you mind leading the stretch break?
Yeah, you're making me get out from under my blanket.
All right, so we are back. So let's look now at how these different methods are performing. So basically adding some noise, or perhaps modifying the backpropagation algorithm to be able to better capture smoother gradients. Okay, so basically, again, we have three hypotheses here where the attribution method assigns attribution scores to every input pixel. Some saliency maps that we can build based on a baseline attribution method end up being very noisy. And we have three hypotheses. One is that truly all of these pixels contribute equally as much as the pixels in the gazelle. The second one is that the gradients are perhaps discontinuous or the function saturates. And then we're going to look at solutions where we're going to change either the gradients or the backprop or include multiple images with some added noise to get around these challenges. And there's many additional attribution methods we're not going to be looking at. So one of them is, the gradient star times input. So basically, if you just have the gradient, you have this very noisy function. But if you multiply that gradient by the input, you end up having a much cleaner representation. You can also integrate the gradient, and you can sort of read about that there. You can do layer-wise relevance propagation. So you can basically, instead of looking at relevance only across the whole image, you can basically look at relevance at multiple layers. You can use Taylor decomposition. Deep lift is something that we're going to actually return to when we start looking at these gene regulatory models for interpreting regulatory motifs in sequences. And then there's also pattern net and pattern attribution that you can read about here. Okay, so let's now look at these ways of actually smoothing the gradients. Okay, so based on hypothesis 2, namely that the gradients are discontinuous, we could just try smoothing out the gradient. So we can basically define a smooth gradient function that is instead looking at the integral over many, many different samples of near x, where we're adding some Gaussian noise next to x. So basically, this is these random small perturbations, and then looking at the average of those small perturbations. And then the idea is that, even though our gradient is extremely jagged, by smoothing this function, we're actually going to smooth the gradient to go back to as if it was a shallow network rather than a very deep network. Okay, so who's with me for this particular idea of adding these perturbations and then integrating over these perturbations, effectively having the effect of, moving up and down these over many examples and eventually leading to a smoother function. Awesome. So 52, 33, 15, 0, 0. All right, so indeed, as you start adding some noise, basically, if the noise level is 0, you basically see that the activation is indeed happening all over. And you're like, okay, well, great. That's probably that, the grass is just as informative as, the particular GNU here that we're looking at. But by adding noise, what you can see is that over many different slightly perturbed versions of my image, I can basically see that the horns are always getting, not always, but are much more frequently than the background getting classified as, or adding to that classification. And you can see here that even with 20% noise, you can kind of see that the signal that was previously very diffuse is now starting to accumulate on top of that particular image. And that's very exciting. It basically says that random noise perturbation, again, this is not adversarial noise, this is random noise. Random noise perturbations are basically still leading to the same classification and are demonstrating in many ways the robustness of the model. But they're also demonstrating that what we've learned through our sort of representation learning, through the many different layers of representations, is in fact a concept of a GNU that is very reliable and very robust to these perturbations. And in fact, for any one image, it's, yes, certainly noisy, but making the right classification. But across many slightly perturbed versions of the image, you can kind of see that the salient features that it utilizes are in fact recurrently falling within the animal itself. That basically, all of these surrounding ones were simply because that one image was basically leading to this noisy gradient relative to the dx of one particular image. But that noisy gradient, which is visualized as noisy here by having pixels all over the place, is in fact smoothed out into the actual image by adding random fluctuations of my image and sampling over them through additional noise adding. Okay, so let's see who feels that they are learning stuff here. So up. All right, very cool. So we have 61% at 5, 36% at 4, 0, 0, and then at 1. I still don't see why the professor is so excited. Hold on, stay strong. Don't let me influence you into getting excited about the material here. All right, so that was hypothesis number 2, that in fact the gradients are discontinuous with any one particular image, but by taking a sample of multiple images surrounding that one, we're actually going to get a smoother gradient. And indeed, this hypothesis appears to be true. The third hypothesis was that this function in fact saturates. That basically this, x here is just, beyond the maximum possible activation. I can only get so excited about a particular deer, and after that, I just, don't get any more, excitement about sort of seeing a deer. So what we could do is in fact scale back the x. So instead of sort of saturating and being in the regime outside the response curve, we could basically bring it back by scaling it, but simply, rescaling the image to not be as saturating, to basically bring back the x to something closer to the, distribution of functions. So instead of having something that's like enormously like a deer, we can kind of, scale back these activations to bring it closer. And that's what this interior gradient is doing. It's basically saying instead of having extreme, I'm going to sort of bring it back closer to where my curve is still integratable beyond, the point, like closer to the point of before the point of saturation. And then you can basically see that by sort of changing this gradient by taking the scaled version with some sort of reduced version of that gradient, as I scale it to 0.02, 0.04, 0.06, etc., I can basically, sort of, if I don't scale it and I say, well, what are the activations that lead to the capture of a camera, then, this is not quite interpretable. But by bringing it back further, even to like 2/100ths of the original activation, then the salient features are starting to appear. And, perhaps you would argue that this is the best, or maybe this is the best, and so on and so forth. But you can see that it's clearly, sort of perhaps brought back from this saturation space. Okay, so who's with me on this concept here? So basically, the third hypothesis was that the gradient was in fact saturated, and one way is to scale the images back in sort of the space that they're still interpretable as such, and then by rescaling the pixels of the image to not be so extreme, you're kind of bringing the image back to the differentiable space. All right, so 22, 52, 20, and then 4 and 4. I guess we're going to have to review some of that in restation. All right, so we're now talking about interpreting these decisions, and we looked at these gradient-based methods and these basically smoothing the gradient or taking the interior gradient. And now let's look at backprop-based methods, where we can actually look at not just convolutional neural networks, but actually deconvolutional neural networks. So basically reversing the operation of these convolutional filters, and then also guided backpropagation. So again, the challenge here is that doing backpropagation through this rectified linear unit basically means that our derivative is going to be 0 throughout an enormous chunk of the space. So as we're doing our forward pass, we're going to be able to sort of take these zeroed out values that are suddenly, not very useful. So basically that's what ReLU is doing. This rectified linear unit is basically zeroing out all of the features below our activation threshold and then simply returning the input function above our activation threshold. Okay. So, and then, the representation of that is this. But then the challenge, of course, that in the in the backward pass, backpropagation is basically, no longer able to recover these zeros, and all of these gradients are sort of not functioning anymore. So what deconvolutional neural networks are doing is mapping the feature patterns to the input space by reconstructing the image. And then to obtain a valid feature reconstruction, they pass the reconstructed signal through the ReLUs again, and then they remove the noise by removing the negative gradient. So in the forward pass, you would sort of lose out your gradient. In the backward pass, you can no longer differentiate through that to generate your images. But with the deconvolutional approach, you're basically forcing your gradient to work in the opposite way as well. So instead of taking the ReLU only the forward direction, you're now starting to take the ReLU in the opposite direction as well. And that's actually removing your negative gradients and sort of maintaining only the positive gradients. And that actually allows you to effectively construct images that are representative of the original image. So you can now combine this deconvolutional neural network with backpropagation, remove the negative gradient, and then consider the forward activations to those images again. So basically in the forward pass, you basically have, this ReLU of zeroing out those. In the backward pass, you have this backpropagation where you're, moving back from these gradients. And then with the deconvolution, you're zeroing out all of your negative gradients. And then with guided backpropagation, you're combining this information gathered from the forward pass of where should I zero out my input, and then guiding the backpropagation accordingly to remove the negative gradient and then consider these forward activations. So if you look at just backpropagation, you basically have, sort of what made me decide that this is a cat. You have this saliency activation map that is basically saying, oh, well, there's something somewhere in this whole image. With deconvolution alone, you're basically generating images that will that are triggering the concept of a cat most strongly, and therefore generating images backward through your convolutional filter. And by using this guided backprop that is combining the sort of forward pass filter with this gradient backpropagation, you're actually guiding the backpropagation specifically to the features that are strongest to activation. Okay. So again, we're going to review those in recitation tomorrow or Friday. So let's now look at how we can actually evaluate these attribution methods. So basically, we're going to look at both qualitative and quantitative ways of evaluating these attributions. So, just to review, what we have is a deep neural network that is making a prediction about a particular class. And then we're asking what were the features of the input that were responsible for that particular classification. So now we saw, we're going to look at evaluation methods that are both qualitative based on coherence and class sensitivity, as well as quantitative based on selectivity, and then remove one and retrain, or keep and retrain. Okay. So let's look at coherence first. So the attributions that we talked about should be falling, basically these attribution scores, should be falling on discriminative features, namely the object of interest. And if you look at the different methods that we talked about deep lift, which we're going to review in a couple of lectures. We talked about saliency maps and smooth grad, and then taking the gradient times the input and other ways of constructing these. And you can see how well these are capturing the specific pixels that are responsible for, say, electric guitar. So here, the Vargrad method is actually capturing that very well. For a quill pen, you can sort of see the features here capturing the pen very nicely, or the dog. Some of them are leaking into the owner, and the deep lift method here is capturing the beetle, but other methods are sort of leaking out onto the surrounding. So you can evaluate how concentrated are these attribution scores to the object of interest. You can basically ask how sensitive are these attributions to the particular class label. So if you're trying to distinguish, for example, tiger cat for a bull mastiff, for example, you can see whether the positive versus negative attribution scores for each class are in fact distinguishing the two classes, or whether they're blending into each other. And you can see, for example, here how smooth grad appears to be separating these classes, very, very strongly. So these are quantitative ways of asking, number one, am I falling in the right pixels? Number two, as I distinguish different classes, are the gradients of positive versus negative scores for the two classes sort of located where I would expect them to be? You can also look at the selectivity of those methods. You can basically remove individual features with high attribution and then see if indeed they cause a large decrease in the class probability. So you can basically sort all pixels based on their attribution values, and then remove individual pixels that are the most informative, and then evaluate the classification function, and then measure how much is my classification score decreasing by removing the pixels that have the highest attribution value. And if indeed it decreases maximally based on the pixels that were given the maximum attribution score, then I know that my particular method of attribution is performing well. So this is the pixel flipping procedure, where basically I can say, okay, well, I have a 2, a 1, and a 0, and I'm going to flip pixels that have the maximum attribution score and see how the classification changes. So here I, can iteratively remove the features that are still being utilized, and then end up with numbers, with digits, with images where the digits are no longer recognizable because I have maximally erased the features that were the most informative. And I can ask, based on the number of features, the number of pixels that I have removed, how much did my classification score drop? And you can see here that with 3 different methods of this classification accuracy, by sorting the pixels according to saliency, I am dropping very, very rapidly, and then I only have a relatively small later drop. Whereas if I was staying stable and then dropping later on, it would basically tell me that my attribution scores are not sorting the images sufficiently well. Okay, so let's see who's with me on this concept here of sorting based on the saliency, and then asking, do I indeed see a maximum decrease in the score based on the features that were removed that were maximally salient? Okay, so we're at 50-50-4-0-0. And then you can see this as, over a larger classification panel, as I'm, removing 30 pixels or 100 pixels, how this classification score is in fact decreasing based on how many flips. And then the area over the curve basically tells you just how fast you're able to decrease. And if saliency feature is very strong, you should be able to sort of decrease very, very rapidly and then stay flat. And that would give you a higher area over the curve. And if you decrease very slowly, it will give you a smaller area over the curve. So basically your accuracy of saliency attributions and classification attributions are in fact can be measured quantitatively using this curve. And then the last part is removing and retraining. So basically sensitivity might not be accurate. The class probability might decrease because the deep neural network has never seen such an image. But instead, what you can do is actually remove and retrain or keep and retrain. So measure how the performance of the classifier changes as specific features are removed based on the attribution method. And then the remove and replace score is basically asking if I replace n% of the pixels that are estimated to be the most important, or if I replace n% of the pixels that are estimated to be the least important, and I retrain my deep neural network and measure the change of accuracy, then what do I find? And then this is basically telling you, here's my original input with a class prediction. I can then use that to estimate using some kind of attribution method, what are the pixels that are the most informative. I can then modify that input according to the estimate by blanking out the most informative, the most salient features, and then see how well is my model doing in the revised image, and then predicting accordingly. And then you can see here how these remove and retrain, or these keep and retrain, are in fact performing, and that gives you another quantitative metric for evaluating your the accuracy of your interpretation for that decision. So to recap, what we talked about today was why interpretability is so important. How do we convert this implicit neural network information that is being captured to human interpretable information? The motivation being that we can verify that the model works as intended. We can debug the classifier. We can make new discoveries, get new insights as to why and how is this model working, but also why and how should we understand particular radiology images or particular games like Go and chess, and also the right to explanation. We saw both anti-hoc methods for training models that are only interpretable, but then there's a huge challenge there of power, and post-hoc methods, which are by far the most common, which are building complex models and then after the fact interpreting them with different degrees of locality. We then saw two approaches. One of them was interpreting the models, which is a macroscopic approach of understanding the internals of the model, versus interpreting the decisions, which is microscopic and focusing on the practical application. For the macroscopic of interpreting the models, we saw how the weight visualizations of a deep neural network interpretation of a car, for example, or a set of images related to, I don't know, houses or cars or people, can in fact learn these intermediate features and visualize these features directly, giving us a glimpse inside the internal workings of the model. How we can build surrogate models that are trained not on the real world complexity, but on the classification decisions of the model. And we saw activation maximization, a very, very powerful technique that basically allows us to say, what are the inputs that maximally trigger the category goose, for example. But then beyond this maximization of an activation that gave us these features that were quite uninterpretable, these images that were quite uninterpretable, we saw how we can, in fact, constrain those features of activation maximization, constrain those images to be sampled directly from the high density areas of the input model. And that gave us much more interpretable images of shorts and, goose and so on and so forth. And we also saw example-based methods for interpreting these models. And then beyond interpreting the models, we saw how to interpret decisions using specific examples that were part of the training set that led to the training, the learned model making a particular decision. You can say, well, I denied your lawsuit because of these particular cases that I learned. And then that allows you to start interpreting the decision of a model rather than the internal representations of the model. We saw different ways of attribution and how the pixels were in fact quite flanking the image in many cases. And then we had multiple hypotheses why the gradients are so noisy. And then we saw ways of smoothing the gradients by sampling perturbations of our image, then bringing the gradient to be smoother, and then converging those pixels from this very diffuse to sort of pixels on the image itself that were recurrently hit through these perturbations. And then how saturation can be brought back by rescaling the image and then sort of bringing it to a place where the gradients are still smooth before the point of saturation. And then how we can use backpropagation, like deconvolution and guided backpropagation, to basically constrain the models and find the most salient features that were responsible for decisions on particular images. And then we saw multiple ways of scoring these distribution methods, where we can highlight the most discriminative features or the objects of interest. We saw coherence and class sensitivity, as well as quantitative metrics of removing features with high attribution and then seeing how large is the decrease in the class probability, and then the remove and retrain methods, where we can remove individual pixels, retrain, and then measure the drop in accuracy. All right, let's see who feels that they've learned something today. Great. So we are at 70%, 30%, 0, 0, 0. And then lastly, who feels that they followed the overall lecture so far? Awesome. So again, we're going to review some of those topics in recitation, but it feels that you guys are pretty with me so far. Awesome. So 25, 60, 17, 0, 0. Awesome. Well, thanks everyone. And I will see you on Thursday for the last of the deep learning theory lectures before we dive into health and genomics. Thanks everyone.